Good day, 10Cs, and welcome to our new unit, Chapter 7, Systems of Linear Equations. Systems of linear equations. Well, what we're looking at here is we're going to be doing some algebra, but we have to consider what we did in previous math courses. Previous math courses, we could have a whole bunch of information in a question, lots of steps. The fact it's an equation is because there's an equal sign, but we could have all sorts of goofy things on either side. So lots of stuff, brackets to get rid of, combining that has to be done. You could have fractions incorporated in it. But what's important in what we did in the past is that we only had one kind of variable in order to solve when we did algebra. We just had to solve for x. And what did we need to do? Well, we needed to do all kinds of math so we could end up with an x equal to a value. That's what this whole thing was about. What can I figure out x is so that if I put x in, I would then have a left side of an equation equal to the right side. That's what algebra is all about. Solve for x so that when x gets plugged back in, the left side equals the right side. Well, now we have systems of equations. And if you go to page 2 of your notes book, the big difference with a system of equation, as we can see here, is we now have two equations that we need to solve stuff for. So in this case, we have y is equal to 3x. Should be a plus 5, not an equal 5. Sorry. Y equals 3x plus 5. And we have 6x minus 5y equals negative 43. Well, this is a system of equations because we now have two equations. But the other reason in why two equations come into play is we now have two variables that we're going to have to solve for. Like we showed back here, this question, we only had an x. But now we're looking at a system, so there's x's and y's, or a's and b's, or the fact that there's two variables within a system. Well, before we start solving systems, let's actually just look at what we do to make sure that the solutions we have are a solution. So what this question is saying is here's our system of equations, and we're saying 1/8 ordered pair, remember, x, y always. We're saying in this case we believe x is 1 and y is 8. Well, in order to know if that's true, that when I plug a 1 in for x, the left side should equal the right side. When I plug the 1 in for x, it should work out left side equals right side. But it's not only an x we plug in, we'd also have to plug in that y. So we have to verify and make sure that the variables that have been identified are the solutions. So I'm going to take my y equals 3x plus 5, but I'm going to substitute the appropriate xy value in and see if it's true. So y now we think is 8, and that equals 3 times x. So 3 times 1 plus 5. Remember, when you're verifying, you're not moving stuff around. We simply want to show and calculate the left and right side separate. Well, the left side is 8. We don't have to calculate anything, but order of ops here, 3 times 1 is 3 plus 5. So we get a left side of 8. We get a right side of 8. 8 equals 8. That's a good thing. Does that mean 1 and 8 is the solution? Well, it doesn't mean yet it's the solution because this 1/8 has to work for both equations. So I have to always, whenever we're doing a verification of a solution, you have to make sure you're verifying in both or all equations. So I need to now verify the 6x minus 5y equals negative 43. So I'm going to plug the 1 in for x again. 6 times 1, because that's what we think x is. Subtract 5 times y. Well, we believe y is 8, and we want it to equal negative 43. So, again, we want to solve left side, right side separate. We don't have to do any solving on the right side. Negative 43. If I do order of ops on the left side, though, to see what it equals, multiplications first. 6, subtract 40, change if it helps. 6 and a negative 40 is negative 34. Is negative 34 equal to negative 43? It's not. So our 1/8, even though it worked in the first solution, it didn't work in the second. So 1/8 is not a possible solution. So let's try B. We have to substitute into the same two equations, except now x negative 5, y 3 has to go into each equation. So our first equation, y, which is now 3, equals 3 times x, which is 3 times negative 5, plus 5. So solve the right side. I want to solve each side separate. Negative 15 plus 5 gives us negative 10. And on this side we have a 3. 3 does not equal negative 10. So do I even have to bother verifying those there? Why? We know that the negative 5, 3 doesn't work for the first equation, so that's definitely not a solution. So this is what we're looking at doing. We have to, as we've done all along, substitute, but we have to substitute into both. Skip and try D. Pause the video, substitute in, see what you get. And please, again, I apologize, this is a 3x plus 5, not 3x equals 5. Pause the video, substitute here, see if this now is going to be the correct solution. So what we're looking at, again, x, y are our values. First equation, y is 11, 3 times x plus 5. We have 11 on the left side, 6 plus 5. We get 11 equal to 11. So the left side equals the right side, and that's a good thing. But even though that's good, this has to work in the second equation as well. So 6 times x, which is 2, subtract 5 times y, which is 11. We want that to equal negative 43, because that's what our right side is. 6 times 2 is 12. Subtract 5 times 11 is 55. 12, subtract 55. What does that give us? There's our negative 43. So negative 43 equals negative 43. Left side equals right side. So 211 is the solution for that system of equations. Real long example, but get the idea that when you're verifying, you have to verify in all systems. All right, on to page 3, developing systems of equations. Word problems are a big part of this unit. Understanding that to create systems, we can create real life situations. So we're not going to solve the systems yet. We just want to look at how do we create, developing the system of equations. And there's two things we have to be careful of. First of all, we're now creating two equations because it's a system. Just like the first example we did where we verified, our word problem is going to involve two equations, not just one. The second thing is we're now allowed to have two different variables. X and Y is usually pretty common. You can use whatever variables you want. But we need to always start by identifying the variables. List them, X and Y, and identify what they represent. X could be the number of dogs. Y could be the number of rhinoceroses. if that's what the question involves. But always start by identifying what your X and Y is, and then you use that information and you create some form of a system based on what the rest of the question says. So that's what we're looking at doing. All right, take a look at a couple examples here. Number one, the perimeter of a sheet of paper is 38 inches. The length is 3 inches more than its width. Bob measured the paper to be 11 by 8 inches. Model the problem, and is Bob correct? Well, the first thing we want to do is we want to model the problem. So what don't we know? Like, forget what Bob measured. This isn't important right now. We want to model what's happening. What don't we know? We don't know the length or the width. That's what our unknowns are. So that's what we're going to have to use as X and Y, because there's two things we don't know. So that's what we're going to identify. Once we know that, now we need to create two equations. We need to find two pieces of information that's going to help us with that. Well, here's the first bit. Perimeter of a sheet of paper is 38 inches. If you have a sheet of paper, what's important? Perimeter is adding up all the sides. You have to add all four sides. So in this case, the perimeter is, well, the length, and we have two lengths. So that means we have 2 times x, because there's 2 lengths, plus 2 y's, because there's 2 widths. There's my first equation. But before that, though, even, we know the perimeter is 38, so I'm not even going to put a p in there. I'm going to put 38. The perimeter is 2 of the lengths plus 2 of the widths, but we don't know length and width, so there's our X and Y. The second piece of information given to us is the fact that the length is 3 more than the width. Well, how can we write that? I always look at this word is as an equal sign. So I look at this as saying the length, which we had called X, the length is equal to 3 more than the width, which we've called Y. Now, there's other ways you can do that. The fact that the length is 3 more than the width, some of you might say, well, if I take the length and subtract 3, I'll get the width. That'll work as well. A lot of times you have options in these. As long as you can justify it mathematically and create the system, you're okay. So that's what the system would look like. Now, this particular question said, well, Bob measured it and says it was 11 by 8. Is he correct? Well, that's just asking for a verification. So let's practice our verifying. To verify, Bob says the paper is 11 by 8 inches. Well, the length is 11, the width is 8. So if I verify in my first, 38 should equal 2 times 11 plus 2 times 8, because my X and Y we think are 11 and 8. 38 equals 22 plus 16, which is 38. Left side equals right side, so we're okay when we verify the first. Now we can verify the second, saying X is equal to 3 plus Y. X, our length, should be 3 plus Y. 11 equals 11. So again, left side equals right side. There's the system, and Bob has the correct answer of 11 by 8. But creating the system and being able to verify. Question 2 here. School district has buses that carry 12 passengers and buses that carry 24 passengers. The total passenger capacity is 780 passengers. So amongst all the buses, they can carry 780 students. There's 20 more small buses than large buses. Well, if I wanted to solve this, we need to create 2 equations after we identify what we don't know. We know there's 2 types of buses and how many they carry, but what don't we know? we don't know specifically how many of each. So we need to call, identify our variables, x and y. And what would x be? X could be the number of, in this case, the number of small buses, 12 passenger. And y could be the number of large 24 passenger buses. So there's my unknowns. It's not how many they carry, but we don't know how many of each they have. So now I need two pieces of information here that I can set up an equation. Well, it says the total passenger capacity is 780. Well, if there's 780 students, we know that we have some students on small buses and we have some students on big buses. Well, we don't know exactly how many. How many students would be on small buses? Well, we're not sure, but we do know there would be 12 students on every small bus. So 12 times, is it 2 buses or 3 buses or 4? We don't know, so there's our x. 12 students times however many small buses there are. Plus, there's going to be some students on the big buses. How many students exactly? We're not sure, but we do know there'll be 24 kids on 1 bus or 2 bus or 3 or 4 or 5 or 10 or whatever. 24 passengers on however many large buses there are. So there's the first equation that we need to work with in our system. 780 total students are going to be made on X number of small buses with 12 passengers each, or Y number of big buses with 24 each. What's the next piece of information that it tells us? There's 20 more small buses than large buses. Well, all kinds of different ways to identify that, but there's 20 more small than large. So that means the number of small buses, X, if there's 20 more, that means the small buses would be the same as large buses plus 20. Because if I just said X equals Y, that's not true. We know there's more small, so I would have to add the 20 to the large to equal the number of small. So X equals Y plus 20. Some students might say, oh, there's a difference of 20 buses, and we know there's more small than large, so I would subtract them to get 20. There's another possibility for that same situation. You have choices at times. Either one would be acceptable. But there's our system of equations. That's what's happening in this question. From there, suppose we're told there are 35 small and 15 large buses. Would this be a solution? Well, we want to verify. And we want to verify, in this case, it's saying there's 35 small. So X, because that's our small, would be 35, and Y, large, would be 15. Well, we plug that into our equations to verify if that's true. X plus Y equals 20. 35 is 15 plus 20. Is that true? Absolutely. 35 equals 35. Left side equals right side. So that's good for our first equation. Then we have our second equation. 780 is equal to 12 times 35 plus 15. Sorry, be consistent here. We have 24 plus 24 large buses. There are students for every 15 large buses there are. That's what it's telling us. Well, when we check this, 780 equals 12 or 35 small buses with 12 kids would be 420 students. 15 large buses with 24 students would be 360 students. And altogether, that would make up 780 students. Left side equals right side. For that equation, when we use 35 and 15. So that is correct. There's the system modeled, and there's what it looks like. So, pause the video, try number 3, and then come back. Let's see what you're able to do on your own. So, stage in the community center is rectangular. Perimeter is 158 feet. The width is 31 less than the length. So what don't we know? We have an X and a Y because we don't know length and width again in this question. That's what we're unsure of, the length and the width specifically. What do we know? We know the perimeter is 158. So perimeter of a rectangular stage would be 2 lengths plus 2 widths. There's our first equation because we know what the perimeter, the distance around the stage would be, so that would be 2 lengths plus the 2 widths. We also know the width is 31 feet less than the length. Different ways to write it. I see this as width, which is y, is equal to 31 less than the length. So we have the length and 31 less than that. There's the system of equations for this situation. Frank determined the stage is 55 feet long, 24 feet wide, length and width. He believes the solution set would be 55 and 24. Quick verification, 158 should equal, verifying the first equation, 2 times 55 plus 2 times the y, which is 24. 158 equals 110 plus 48. Our 158 equals 158. Left side equals right side. So that's correct for our first equation, but we always verify both. In this case, we're saying y, our width of 24, is the length, 55 less 31. Well, 24 equals 55 minus 31. There's your 24. Left side equals right side. So there's the dimensions of the stage. 55 feet by 24 feet. Create the system and verify it. Last one on the next page, 5. This is where you have to be a little creative and think. Here it says a little bit of information, and then it gives you an actual system that you have to state what the variables represent. So a bike has 2 wheels and a trike has 3 wheels. Create a situation that can be modeled by the given system. Identify what each variable could represent. Well, in this case, we have bikes with 2 wheels and we have trikes with 3 wheels. Well, the fact that the variable is b and t can be a bit of a clue, because what does it tell us here? Well, this is just combining things, so we could say that b is the number of bikes and t is the number of trikes. That simple equation, b plus t, that could just be how many of each. So we know there's 40 bikes or trikes in total. That's what it's telling us. But this second one now, what does this tell us? Why would we multiply bikes by 2 and trikes by 3? Well, because that's how many wheels they have. So being able to interpret what's going on is part of this course as well. So in this case, this kind of represents, if B is the number of bikes, this would be the total wheels on bikes. Whereas 3T, 3 wheels for every trike, could be the total wheels on the trike, or on all the trikes. So that's our second piece of information. 40 bikes and trikes in total. And if I take the number of wheels on the bikes and the number of wheels on trikes, that 100 would say there's 100 wheels in total on the bikes and trikes. This is just about being able to interpret the information given to you. It's a skill. Practice it. There you go. There's your assignment. Textbook, page 401. Those questions. It's the start. It's not about solving yet. We're going to get to that. Get her done. Have some fun.